In the course of this video, I'm going to illustrate how a pair of toolbars that are new to this version of CasaXPS can be used to process a data set without recourse to any dialog windows. The toolbars are available from the View menu, and these toolbars provide sufficient functionality to allow the analysis of a data set of spectra that evolve with time into a pair of component curves which represent different chemical states of the sample over the course of this measurement. A linearly squares analysis based on these component curves provides a means of creating a profile showing how the trends change from the initial material to the final material over the course of the experiment. Finally, I will attempt to place into the context of chemistry the mathematically determined shapes from the analysis. In particular, we have one that represents polyvinyl chloride and the other represents the material after chlorine has been lost from the polymer. In this video, I'm going to illustrate how this new toolbar can be used to process data without having to go to the dialog window in the form of the spectrum processing dialog window and switching between the property pages for PCA or the calculator property page or various other property pages that require operations such as merging irregular data. Now, these options that are relevant to the data that I'm going to look at are now all presented on a toolbar. To demonstrate the uses of these toolbar buttons, I'm going to use a data file that has been collected from PVC. So we expect to see carbon and chlorine in the data, and the data file consists of carbon and chlorine VAMAS blocks representing narrow scan spectra for each one of these element transition fields, hence they appear as two columns in the VAMAS file. There is a survey measurement that is actually measured at the end of the sequence, but the evolution or the changes that I would like to analyze using this toolbar are clear within the carbon for sure, and there is some kind of movement that we see in the chlorine. But of particular interest is what happens in the carbon. In the rest of this video, I'm going to make use of this toolbar and the buttons on this toolbar to analyze these data. I'm not going to revert to using the dialog windows. I'm going to demonstrate that for these type of data that these toolbar buttons are sufficient to extract chemical state information out of the spectra. Now, the toolbars that you see here are displayed because of options that are set or enabled or disabled on the View menu. So there are 4 enabled toolbars plus the status bar. And the 2 new toolbars over and above what are in earlier versions of CasaXPS are these 2 here. One represents changes to the display state as we see in the active tile, and these toolbar buttons on the 4th toolbar are the processing options that I'm about to use. So to illustrate how this works, I'm going to look at performing a PCA on the set of carbon monomer spectra. And all I have to do is press the button. There are a set of default values that have been used. They are possibly the same or different from what you see on the dialog windows, but they are designed to apply to a more general data set, and the more specifics of the PCA property page are designed to let you adjust parameters to optimize for different data sets. And that is essentially the difference between what has just happened based on the toolbar versus using the dialog window. There are a few other slight differences. For example, these other buttons here that are related to PCA, they're called AFs, meaning abstract factors, and there's a number on each one of these toolbars indicating the number of abstract factors that we calculated and then used to reproduce data. And when I press one of these buttons, despite the data being in a process form, as you see here from the PCA, it will redo the entire calculation from the raw data. So what I've done is I've calculated 2 abstract factors, and I've reproduced the data using 2 abstract factors. If I press the next one, that would be 3, 4, 5, and each one of these is adding a bit more information back into the calculation of these reproduced data. And this is important for eliminating, to some extent, noise from the data without eliminating too much noise. So these are all PCA options. We could have performed all of these using the PCA property page. There's another button here that is equally on the PCA property page, which is reset, so I can return to the raw state of these data. When we perform operations that involve linear algebra, which is essentially what PCA does, we need to have data that are aligned in binding energy. Not just aligned in binding energy in a visual sense, we need them aligned in a data bin sense, so that an intensity that represents the peak maximum is within the same data bin for all spectra. And this will be a problem if we have some kind of charge compensation that is not uniform for all the measurements. Now when we look at these data, the carbon 1s, we can see changes. We would like to think that these are all chemical changes, but in reality this isn't always the case. That a sample and the potential on the sample may evolve equally as the chemistry evolves as a consequence of instrumental factors. Charge correction, charge compensation is what's required. So if I go to the chlorine 2p, now these represent a chloride peak in PVC, and hopefully this chloride peak is representative of the PVC regardless of the evolution of the sample under the X-rays. So what I'm going to do is make the assumption that any changes that I see here are actually due to charge compensation, and if I correct all spectra on the basis of aligning the peak maximum, then I will have a data set that is one step closer to being able to be used for linear analysis. So I'd like to align these peaks, and there is a toolbar button now that allows me to do this type of alignment. It's not strictly speaking an energy calibration step, because I'm not going to align to a specific binding energy, but rather I'm going to take one of these spectra and use it as the energy against which I will move all other spectra in order to produce an alignment of these chlorine 2p peaks. And I can do this using an option that creates from a region a peak position. And what I've done is I've used a polynomial regression type to calculate a peak maximum. Now I don't have to use a polynomial regression type to find this peak maximum. It might be more appropriate to use a peak model, but by just simply using a region I can do this operation quickly and in this case effectively. So all I have to do is create this polynomial regression type. It initialized the cross section so that I have a polynomial with 14 coefficients, and it's found a peak maximum for one of these spectra, and when I propagate the region to other spectra that are selected, and the selected spectra are these chlorine 2p, then I should have a background with a sufficiently good position for this peak maximum for all of these data that I can now align the spectra with respect to this peak. This is a chlorine 2p 3/2 peak, and the toolbar button align energy scale. When I press this, then we end up with an alignment of the spectra. Now this is the same action as you would perform on the calibration property page using the apply by row first region. The only difference is I didn't specify a measured and I didn't specify a true. I simply took those two values based on the first spectrum, so you'll find that they have an identical value. If I look at the processing history, you can see that for the first spectrum that is displayed in this active tile, the calibration is effectively a null calibration in the sense that the measured and the actual value are both identical. However, for all of these other spectra that was selected, a new measured value is calculated from the peak, maximum from the region, and that is used to shift the spectra relative to the first one, and this shift will then be applied to the carbon in the same row. So not only are these chlorine 2p all aligned, but in principle all of the carbon will also be aligned, and that does appear to be the case. Now, why do I think that is true? I think that's true because if I look at the peak that is within this carbon 1s envelope, I believe that the highest binding energy for the carbon will be achieved when the carbon is bonded to the chlorine. So I have got, to some extent, a correlation of binding energy from the chlorine 2p with the binding energy for the carbon 1s that is bonded to the chlorine. So having calibrated all of these spectra, what I need to do now is create from these calibrated spectra a set of spectra that have been reassigned intensity to data bins so that they all correlate intensity with a specific data bin and a specific binding energy. The calibration that has been performed based on a shift in the binding energy for each individual spectrum without making any adjustments to the intensity, so as they stand they would not be suitable for doing PCA or any kind of linear analysis. Now there's a button on the toolbar which rebins the spectra, so all I have to do now is select, as I have done, the two columns of spectra that I would like rebinned, and when I press the rebin, what will happen is it will create a new file in which we have spectra that are all aligned. Ultimately, what I would like to do is create a profile from these data that illustrates how the carbon and the chlorine changes as a function of the measurement. And to do that, I would like to use these buttons that are currently grayed out. Now these apply to data that have been converted through the quantification parameters dialog window using the report spec page to create a profile of regions or components or some aspect of a set of data that can be plotted against an independent variable. And the independent variable should be this number here. Now we see in this rebin form all of these values are set to 0. Now that's not going to be useful when I try to create a depth profile, so I'm going to take a step backwards. I'm going to delete this file, and now that I've got my original file again that is calibrated, just verify that's the case, yes, I've got the calibration information in this file, so I can perform that rebin operation again. However, before I do the rebin operation, what I'm going to do is use another toolbar button on the new toolbar that says next experimental variable. When I click here, because these data were converted from a Vision 2 data set using a cal format, a number of different experimental variables have been assigned to each one of these VAMAS blocks. I've just switched from what was the etch time, and there was no etch time because this was not an etch experiment, so they're all 0, to the position index. Now this is interesting because it's the same index number, therefore this is the same position. So that's information that's useful. If I click again, I get the angle. Well, there was no tilt with any of these measurements. Sputter time, well, it's identical to the etch time in the sense that no etching was performed. And then there's a date stamp. And now I have a sequence of values for the experimental variable that are indices that represent the individual measurements that were performed. So now if I select my calibrated data, calibrated in the sense of shifting the energy scale, I now want to do the rebinning once again. So now I am aligning intensity with the energy scale, and so I have an experimental variable that is 1, 2, etc., representing each cycle. So let's just verify that we have the same data again. Yes, we do. They all align in terms of the chlorine 2p3 halves. So we're now in a position to do some linear algebra on these data and make use of these toolbar buttons to create profiles from these data. The data in this rebin file are in a state where we can apply PCA and reconstruction using abstract factors and ultimately perform some linear analysis to fit curves that we will generate from these data. But we first need to try and create these component curves that represent hopefully different chemistries within the sample that happen to occur as a consequence of the measurement process. Well, the first thing I can do is display the residual and look at these data when I reconstruct the data using different numbers of abstract factors. I could perform a principal component analysis on these data and see that there is predominantly one shape and there's some minor shape here, and that gives me hope that I can reproduce these data using just 2 abstract factors. And the key point is that I end up with oscillations in a residual, and this residual represents the difference between the original data and the PCA enhanced data. So right now that looks reasonably good. I've seen better, but it looks reasonably good. What I'll be looking for is a uniform distribution and a residual standard deviation that's somewhere in the region of unity. And this was with 2 abstract factors reconstructing the data. If I use 3, well, then I get something that looks a lot more like unity and slightly improved perhaps residual plot. So I might accept this as being a reasonable way to reproduce these data using abstract factors. Let's have a look at the carbon 1s. The residual plot is there. Let's try 2. That's close. Let's say 3. It's about the same. So I'm going to go with 2 abstract factors here. So now I've created reproduced data. You can see that the residual represents the type of noise that has been removed by reproducing using 2 abstract factors or 3 abstract factors. This means that the quality of the data that I'm about to use in a difference calculation will be superior to the original raw data. Now, having created these what I hope are superior spectra, I'm going to use another display option on this processing toolbar. It is a display option, but what the toolbar does is it collects together all the relevant operations that you might want to perform on data en route to this type of analysis. So hence, when I press this button, although it does also exist on another toolbar button, it's here and available for processing of data of this form. So now, having obtained spectra taken in pairs corresponding to each row of this data file, they are now displayed 2 per tile, carbon and chlorine. And as I do this, it's in a state where I could use this option, which I would have had to gone to previously on the test data property page, to merge spectra to produce spectra that would show me how the carbon and the chlorine change within different spectra. I can now do this using a toolbar button here. Merge irregular. This is the same operation. It requires spectra to be overlaid on a row by row basis in the tiles, and for each tile in the scroll list a new VAMAS block will be created. So I'll press this button and create the new file with the new VAMAS blocks. There we have it. We now have our data organized so that we've got noise reduced data that we can use to create component curves that ultimately, hopefully, will show us some insight into the chemistry of what happens to PVC as it degrades. The way we can understand how the PVC degrades is to take these data that are overlaid in the active tile and choose two of them to perform a difference calculation. So ideally we want to choose two spectra that are the greatest distance apart in some sense. In fact, it's the angle between these two vectors in a vector sense that makes the biggest difference. So in terms of this data set, the two spectra with the greatest variation will be the first and the last. Now previously, if I wanted to do a difference calculation using the calculator property page, I would have to overlay two spectra. In this case, I've overlaid all of these spectra, and they are overlaid in an order, in the order that they were selected in the right hand side, which means that the first one and the last one actually represent the greatest variation. And this happens sufficiently often that when I overlay data in the active tile and view the data, the difference that I want to calculate is from the first and the last. And that's what this difference toolbar button does. It performs a difference calculation that is based on the first and the last that was selected out of the data that are displayed in the active tile. So when I press this, the toolbar button converts the set of spectra, taking the first and the last, into a list that corresponds to the difference between the first and the last, with incremental changes in the magnitude of the first and the last in that difference. So when I scan down this list, I can see what happens to the data. Now what's happening is I'm looking at the carbon 1s, about 280 EV, and at this point I see that there's a non-physical shape appearing in the data, this point here. So that suggests that I've gone too far in taking away the last from the first. So I'm not quite sure at what point I should choose a different spectrum out of this list, but a good idea can be gained by looking at this part here of the spectrum, because the lowest binding energy is often a clear indication of where a peak begins to emerge from the background. So that's always a good place to look, and it ought to be true here too. So if I zoom into the chlorine, I don't see any anomalies here. I'm quite happy that this is one possible candidate for the decomposition of these data. Now I can copy this selected VAMAS block using a toolbar button. Copy VAMAS block to new column. This was also an option available on the PCA property page, and when I press the button I get a copy dialog window, and when I accept that copy I get a new column, and it has the VAMAS block that I've just selected moved out by one place. This is helping me keep track of where I am in the calculation, and it is selected, so I can use the arrow keys and step back to the list, and then I can continue down the list looking for the opposing type of spectral shape that will be the opposite in the list, in the difference list, that will represent the alternative state within these data. And now we can see, as I continue down this list, that a peak, a negative peak grows, then it becomes positive in the carbon 1s, and ultimately I end up with something that looks quite reasonable for a carbon 1s. But I don't really end up with something reasonable in the form of a chlorine 2p. So if I keep moving down the list, I'm using the arrow keys, I see that I do have a chlorine peak emerging, Let's have a look at what the carbon looks like. Well, it hasn't particularly changed too much, so I will carry on going down a bit, and well, I now have another possible curve, and I'm going to call it a curve because these are spectral shapes, but they're component curves that I'm going to use in a least squares calculation. So if I decide this one is also useful to me, I'll take a copy of that one as I did before. So now I have two VAMAS blocks. Each one contains a different curve, and fortunately these two different curves give me the idea that I've got different chemistry. I see a shift in the carbon, so if that was the CH part of a PVC polymer, then what has happened is another carbon peak has emerged at a significantly lower binding energy that makes me believe this represents a different state for carbon within the material after the degradation has occurred. Now, how can I justify what I've got over here? Well, in terms of the chlorine, I have one chlorine peak which is very well defined. I would suspect this is representative of the PVC in a pure state without any degradation. It's never going to be perfectly pure. We would have to have very ideal data to be able to distinguish between different chemical states without any overlap whatsoever. But as we look at these data here, there's one that is definitely looking like PVC, and the other one looks like chlorine in some other form. So let's just have a look at these as I overlay them. It's not too dissimilar. What is different about these two chlorine peaks is the background. So one has to ask the question, why would the background be different? Slightly broader perhaps. This could be instrumental factors. Nevertheless, what it looks like is we've got chlorine in a chloride state, and we've got carbon in states that would be compatible with PVC and a state that is compatible with not being in PVC. So this blue curve could represent the degradation product. I need to keep track of these component curves, so I will first of all align these in terms of the right hand side, and that is achieved by using the same element transition field for both of these VAMAS blocks. They will then appear in the same column in the right hand side. So that's the first step, and they appear in the list in an inconvenient way, so I'm going to move these two curves to a new file so I have only these two curves, and now I have a VAMAS file which I can easily access when I want to use these component curves in some other calculation. Now what I'd like to do is fit these component curves to the rebin data in the raw state, not the process state. So if I take these and I overlay all of these VAMAS blocks in the active tile and reset, then display on a row by row basis, so I've got my carbon and my chlorine organized as I did before, and then merge these in this state, I will get a new VAMAS file that contains merged data that is raw and not the processed. So this is what I'd like to fit my component curves to in order to evaluate how well I did when I chose my component curves. So let's go back to the new file. Here it is. It contains the two component curves. I go to my newly created merged data from the raw state, copy the two selected VAMAS blocks into my merged data file. So now I have the component curves that I'd like to analyze all of these data into these component curves using linear least squares. So this is exactly how I would have to set up for a least squares calculation if I was using the principal component analysis property page on Spectrum Processing. But now I have both my component curves overlaid, the targets, the spectra that I'm going to decompose into these component curves, and there's a toolbar button, linear analysis, and this will perform the same operation. So two basis spectra, a set of target spectra, press the LA button and we get the same dialog window suggesting that we've got two basis, 66 target, and we say yes, do you want to continue? Yes, we do. And a new file is created that contains the original data. So these are now the raw data. The least squares curve that is formed by the sum of these two component curves. So when I display per row, you can see now the decomposition, and if I step down through this data set, all of these least squares calculations are showing how the different proportions of these two components are used to make up the original data. So they're fitting in a linear least squares sense. I'll now illustrate how these grayed out buttons work for creating a profile from data such as these. And the idea is that we must create some kind of quantification item on these spectra, these component curves, that make some kind of physical sense. So let's use the element library and we'll create regions by having the quantification parameters dialog window with the regions property page topmost, and then click, and I've selected zoom when line selected, create when line selected, and I select the carbon 1s line, and it comes in with the polynomial regression type that I had previously used. So I'm going to change that to be a 2GAR approximation, and that's because I'm dealing mostly here with polymers, and this is set up with polymer coefficients by default, so it may not be the most appropriate, but it'll be good enough for what I'm going to illustrate here. So I've created a region that represents the carbon 1s, and if I move these out of the way so I can see, I can also create a chlorine 2p, and it will use the 2GAR background because it was the last one used. So there I have two measurements of what I think is PVC in terms of the amount of chlorine and the amount of carbon. So there we have two regions set up for the one component. I need to propagate the region to all of these other components in this file. I need to do the same for the other component. So this is the component curve that represents the degradation product. I will select carbon 1s again and make an adjustment of the region limits so that I've got a background defined, and do the same for the chlorine. And propagate. So that means I will have the same pair of regions and components on all. Now I didn't actually adjust the name, so let's say degradation product. So we differentiate between the signal that we're taking from these two different components. I've changed the name. I don't need to propagate again. I could propagate again, but there is an option that says copy names. So I'll just copy the names without copy the regions. It didn't make any difference in this case. Sometimes it does. So there is a means for propagating the regions, or you can just propagate the names. So now I have in my file a set of valid indices distinguishing between the different measurements, so this is suitable for a profile. And we also have regions and components set up on these two components. So from these two component curves we will get 4 different regions. They won't all be independent because they are linked by the same component curves, but nevertheless it will suggest that we've got 4 different trends within the data. which can be characterized in terms of the area of these peaks, which are corrected by relative sensitivity factors that are defined in the regions. These are not necessarily perfect for this application, but they're good enough to illustrate these toolbar buttons. So having selected all of these, the only ones that have regions on them are the two component curves. I will then press the area report button, which produces a text report showing me the numerical values of these areas for each one of the regions I defined, and from these areas a calculation providing the atomic concentration in some sense. Now what has happened by virtue of creating this text file is that we now have these buttons, at least two of these three buttons, now enabled, and if I press the first or the leftmost of these buttons, it will create a new VAMAS file that contains the profiles. So you can see now that a trend has occurred within the data where the degradation product in terms of the carbon 1s is increasing and the polymer itself in terms of the carbon 1s is decreasing. But there are some tricks that I can also demonstrate now that we've got a profile, is that there are additional toolbar buttons on the display toolbar that will help display profiles. So for example, if I wanted to add points and some information as a key, then that is achieved by pressing this button here. There is a button next to the display of the profile button that just gives a little adjustment to the limits so that we get to see the profile in a little bit more detail, and we could then adjust the intensity so that we have an atomic concentration in terms of the degradation products and the polymer itself. Up to this point I've mostly concentrated on the mechanics and the mathematics associated with creating this profile. Now the aim of this profile is to monitor how the sample degrades, so we can see the degradation product and the original polymer, how it diminishes with time. But to really make these statements you have to look at the component curves and try and understand how much sense can be made of these component curves in terms of chemistry. Now when we look at these component curves and we consider the carbon 1s, this is a binding energy of about 285 eV after it's calibrated perhaps, but what we can see in these data is that the red component curve corresponds to the PVC. So why do I say that? Well, carbon bonded to chlorine. The chlorine is electronegative, so we'd expect electrons from the carbon to be moved towards the chlorine and away from the carbon. Fewer electrons, greater influence of the nucleus, you'd expect the remaining electrons to be bound more tightly, and so we see a greater binding energy for the carbon bonded to chlorine. Then we have another peak that is associated with polyvinyl chloride. This is carbon bonded to hydrogen, but we still have the influence of the chlorine in the carbon that was bonded to chlorine, and this second peak is a carbon that is bonded to that carbon atom bonded to chlorine, so it too is feeling some influence from the chlorine. So one might expect the binding energy to be slightly higher than you'd expect for a polymer that does not involve chlorine, just carbon and hydrogen. Now the second component that is blue, this has a carbon peak which is at a low binding energy relative to both of these. Now this suggests that we do not have chlorine involved in the bonds associated with this component curve. However, that's not entirely true, because we see a structure here and that correlates with the chlorine peak. As I increase the chlorine intensity, so the intensity of this shoulder increased. So I'm unable to remove entirely from the data the influence of chlorine without somehow damaging the shape of the chlorine peak. And you may ask, why do I think there should be a chlorine peak there? Well, the answer is that I believe that as part of this degradation of PVC, that we will see some HCl created. Now that can be created just by heating PVC. So there is certainly a significant chance that we've got some kind of HCl within the material, no carbon bonded to Cl, so there might be some Cl without any correlation with carbon. But I suspect that I've included in this blue component an element of both the HCl and the carbon that is still bonded to chlorine. But we can definitely see that the carbon has arranged itself within this material after degradation, where it's just carbon bonded to carbon or carbon bonded to carbon and hydrogen. And this may be a test case, but this demonstrates that we can gain some kind of chemical understanding of what's happening in a sample, even when we don't expect that chemistry to occur, and we would hopefully not see any chemical changes when we do XPS, but the fact is that we do see changes. So it's good to be able to see the changes and understand what chemistry is being created as a result of measurement by XPS.